Let's start by discussing programming style as it refers to documentation. Documentation refers to a description of what a program does and how it does it. We're going to discuss documentation only in terms of comments added to the program file itself. It is often necessary to develop external documents describing how a program works and how to use it, but we're not going to discuss that here. Now let's start by remembering that comments in Matlab begin with a %sign. Also remember that the first block of comments in an M file, and by block I mean a sequence of consecutive lines beginning with the %sign, has a special meaning in Matlab. It defines the information accessed by the help command. Let's look at an example. I'll start by opening lhs.m. That's my left-hand sum program. You see that I have a block of comments that appears just after the function line. There it is. If I go to the command window now and type help LHS, I see that information displayed. Now let's look at the format of this documentation. I have an initial summary line. I have the calling sequence of the function, in other words, a statement of how to call the function. And then I have a description of what the function does and what the inputs and outputs mean. This description is very brief, but I think all the information is there. This function estimates the integral. What do the inputs mean? Well, we have the integral of f from a to b, so that tells me what the first three inputs mean. I say that it's done by the left-hand rule, and I say that we use n subinterval, so that tells what the fourth input means. I don't explicitly say what I means, but this function estimates the integral. There's only one output, so that output has to be the estimate of the integral. When you write this initial block of comments that's going to be accessed by the help command, make sure that you explain how to call the function, what the inputs mean, what the outputs mean. Also remember that the first line of the first comment block has another use. It's displayed if I type help followed by the folder name. Now my M files for this course are stored in a directory called my M files, so let's type help my M files. What I see is one line for each M file that's in the folder. That line contains the name of the function or script, and it contains this summary from the first line of the comment block. So you see there, for instance, the first entry is LHS. It estimates an integral using the left-hand rule. I strongly urge you when you're writing your M files to take advantage of Matlab's mechanism that allows you to incorporate your M files into the Matlab help system. Now you'll notice that apart from the initial comment block, I don't have any other comments in lhs.m. That's because this is a very short, straightforward program. The initial comment explains that the left-hand sum is used, and anyone who knows what the left-hand sum is will understand the code. It's not the purpose of the comments to define and explain the left-hand rule mathematically. Let's look at an example that's a little more complicated. Quad LHS uses Richardson extrapolation together with LHS to estimate an integral with an error less than a given tolerance. Let's look at the program file. There's the initial comment block, but you'll see that in addition to those initial comments, I've added a few other comments throughout the program code. Now I want you to remember that the help command only displays the first block of comments. So what I've done here is to add some comments that explain what each block of code is doing. First I compute the left-hand sum on the two initial grids. Then I'm going to use Richardson extrapolation to estimate the error in I2. As long as the estimated error is at least tall, I refine the grid and continue. That's what this block of code does. And then finally I explain that the final estimate is found by Richardson extrapolation. And I point out that the estimated error is an estimate of the error in I2. The error in I, which is actually the return value, is expected to be noticeably smaller. Now let's shift gears and talk about testing for and responding to errors in input values. Let's begin with an example. I'm going to use my LHS function to integrate sine on the interval from 0 to 1, and I'll use 100 subintervals. There's the value that I get. And let's suppose I do almost the same thing, but I enter the interval of integration as the interval from 1 to 0 instead of the interval from 0 to 1. According to the usual definition of the Riemann integral, the integral from 1 to 0 should be the negative of the integral from 0 to 1. Therefore, I'd say that the current version of LHS does not respond correctly to the case of an integral from a to b, where b is less than a. If we look at the code and think about it, we can understand what's going on. If b is less than a, then dx, which represents delta x, is negative. Therefore, the values of x that we're using in the Riemann sum are actually a, remember a is the right endpoint of the interval, a minus delta x, a minus 2 delta x, and so forth, down to b plus delta x. we can see that the effect of b less than a is to estimate the desired integral with the correct sign. It has the correct sign because we're multiplying by dx, which is negative. Right here we're multiplying by dx. But the estimate is done by the right-hand rule, not the left-hand rule. This is not what I want to do, so I'll have to modify the code somehow. I see two ways to modify the code. The first is to treat b less than a as an error condition. I don't think this is the best decision, but I'll present it first as an opportunity to introduce the Matlab error function. I will also have to introduce the if statement. I want to modify my program by introducing code that checks to see if b is less than a, and then reports an error condition and terminates the program if it is. This turns out to be straightforward. So here's how it works. The statement is if b is less than a. If that's the case, I want to report an error and terminate the program, and Matlab has a function for doing that, which is appropriately named error. I have to choose an error message. I'm going to say inputs a and b must satisfy a less than or equal to b, and that's the entire if statement. I save my function, and let's try it out. So I'm going to invoke LHS, but I'm going to put b less than a, like so. Matlab does report an error. It tells me there was an error using this M file, LHS. It tells me the line on which the error function occurs, and then it prints my error message. Now you may have noticed that my if statement doesn't handle the case that b equals a. In this case, the correct value of the integral is 0, and that's what the code will produce because dx is equal to 0. However, it's certainly inefficient to do all the computation when the error is known ahead of time. To address this case, I can use an if-else if statement. So that's going to look like this. I add a second clause, else if b equals a. In this case, I want to set I equal to 0. And then I want to return. So here's another new Matlab statement, the return statement. Just like the error statement, it causes the M file that called it to be terminated, and control is returned to the calling program. However, unlike the error statement, there's no error message that's displayed. So now let's suppose I do the integral from 0 to 0. I find out that the answer is 0. Just for emphasis, let's see what happens if I were to do, say, 1,000 subintervals. Doesn't take much time. Suppose I do 10 billion. Still doesn't take much time, because no computation is being done in this case. Now I mentioned earlier that I have two options in handling b less than a. I think it's better not to treat this as an error condition, but rather to make sure that if LHS is called with a and b switched, it returns the same value except with an opposite sign. The point is to make sure that the left-hand sum is computed whether a is less than b or b is less than a. Here's how I do it. So first of all, I'm going to remove this error condition. If b is less than a, I'm going to switch the values of a and b. Notice that I can put a comment at the end of a line if I think that what I'm doing on that line needs to be explained. This is a standard algorithm for swapping the values of two variables. I can't merely say a equals b and b equals a, because after the statement a equals b, the original value of a has been lost. So what I do is I save the original value of a in a temporary variable, then I set a equal to b, and then I set b equal to the temporary variable. Now I need to have some kind of indication that I did this. I'm going to do this by creating a variable m and giving it the value -1. And at the end of this program, I'm simply going to multiply my final value by m. Now, in the case that a is less than b, I don't need to do anything except set m equal to 1. Then the alternate case is that a equals b, and in that case I set I equal to 0 and return. The rest of the code doesn't change, except that at the very end, I equals m times I. Notice the use of the if-else statement. The purpose of this statement is to give multiple options. The else option executes if none of the previous conditions holds. In this example, I only need one else-if condition, but there could be any number of else-if conditions in an if-else-if statement. Now let's test the code. First I'll compute the integral of sine from 0 to 1. Then I'll do the same thing except from 1 to 0. I should get the negative of the same value, which I do. Now I'm integrating the sine, which I can do analytically. That's the exact value. And you see that I have approximately the correct value, correct to 2 decimal places. Finally, let's just check and make sure I'm handling the condition a equals b correctly, and it appears that I am. When you write any program, you have to think about what the purpose of the program is, and in particular how long you're going to be using it. Generally, the longer the life you plan for your program, the more time you should spend writing it, documenting it, and testing it. Also, the more error conditions you should be concerned about. You might notice that in the program we just went over, I was careful to handle the likely unexpected inputs for a and b, namely that b might be less than a. But I did not check the input n to make sure it's reasonable. In this case, we'd have to make sure that it's positive. And I did not check the first input, f, to make sure it's a function. If a user makes a mistake and passes a variable that's not a function, then the program is going to fail somehow, but in a more unpredictable way. If I want to make sure that the program fails gracefully, I have to test for and handle any error conditions. If I'm writing this program as an example and I'm going to be done with it tomorrow, it may not be worth thinking carefully about every possible error condition that might arise. But if I'm going to make this part of a library of functions that I plan to be using for months or years to come, then it would be a good idea for me to be as careful as possible concerning error conditions, and also to make sure that the documentation is crystal clear. A common situation for a programmer is to write a program and then 6 months later go back to modify it and realize that he or she doesn't understand what the program is doing. Good documentation can help you avoid that problem.